Is it raining, Balloon Man?
No, the umbrella is just to keep the sun off my head.
I see. That must explain the sunshades.
Nice.
So are you ready to do the review questions for Module 2, starting with number 6?
I am.
Great. Let's get started. Okay. Please read number 6 to us.
Heat is added to two identical objects that are initially at the same temperature. If the first absorbs 100.0 calories and the second absorbs 100.0 joules, which gets hotter?
100.0 calories and 100.0 joules. So what do we have to know here, Balloon Man? What is the relationship between these? These are two different units of measurement, right? These are units of heat or energy. And so...
Yes, 1 calorie is equivalent to 4.184 joules.
And we could write this equivalence or this one.
Well, it seems to be that the calories are much hotter.
Okay, so yeah, if I have,
we need to answer.
If I have 100 calories, I'll have 400 joules.
Yes.
Okay, and if I have 100 joules, I'll only have about 25. Let's use 4 as an estimate. I'll only have about 25 calories.
Yes.
So 100 joules is equal to 25 calories approximately. Right? So, and the question says, which gets hotter?
It's the one that absorbed 100 calories.
Yeah, this one. Okay. Now please read number 7.
Some diet books tell you that an excellent way to lose weight is to drink ice cold water. Why is this? Well, one answer could be that there's a lot of odd beliefs about dieting.
Can we focus on the chemistry, please? Thank you. What does it have to do with? It has to do with what we were talking about in
energy
things like
loss.
question number 4 or question number 3, right? We're talking about how does temperature change? When an object changes temperature, it's either gaining or losing energy, right?
Yes.
So if I add something cold to my body, in order to maintain my body temperature, I need to heat up that water. And so I'm going to
expend potential energy.
I'm going to burn more energy. I'm going to burn more calories. Calories
more
being
fats.
Right. So is it a very effective way?
I don't think so.
No. But is it true?
Yes.
Yeah, you will actually burn more calories by drinking ice cold water. If you drink too much ice cold water, you can actually literally die. So do be careful. Don't go drinking too much water.
Yeah, hypothermia.
No, it's not hypothermia. It's too much water. I forget what the term is called, but you can look it up. People have died from it. Usually for like a contest. How much water can you drink? It's not just alcohol that can kill you. Water, too much of anything, not a good thing. Please read number 8.
Examine the heating curve for the following unknown substance. So we got a graph with 6 levels, each one in tens, going from 0 up to 60 degrees Celsius. And then at the bottom we have...
Okay, please don't describe it to us. Anyone who should be doing this video will have his or her own book.
Okay.
Okay, so we're on, of course, page 67. So this is the graph that we're looking at. Yeah. At what temperature does this substance boil? What does it mean to boil? Let's just talk about that. We haven't done the experiments yet when we're recording this video for this module, but we will do one and discover that when water is boiling, it will stay at 100 degrees, okay?
Celsius.
In the liquid form, it's not going to get hotter than that. It's going to go into the 100 degrees Celsius, yes. My science class, we always use metric units. Boiling means to be at the highest temperature that it can be. So
as
what's
a liquid.
Right. And so this unknown liquid, When does it melt?
At approximately, you mean when it evaporates?
Yeah, you can
that
see
would
it.
Be, it appears to be around
no, when 55 does it melt?
degrees.
No, when does it melt? It melts around 5 degrees.
15.
That's the bottom line. Okay.
Yes.
So there's a graph that looks like this. Okay. This is when it is solid and it melts. This is what we call the melting point. And this is what we call, boiling up here, the boiling point. Okay, so for water, that will be 0 degrees Celsius, and that will be 100 degrees Celsius, right? So this unknown liquid has a different melting and boiling point than water. So it's a different kind of liquid.
Boiling point appears to be at 55 degrees Celsius.
It does. You could possibly say 56 or 54, depending on where you thought the line was. I think it's pretty clearly at 55. How many marks are on the gradations there?
Well, there's 6.
Yeah, so what is the unit segment between the marks, the tick marks?
1 minute.
I'm talking about the temperature marks. It's every 10 degrees, right?
Oh, yeah.
So if you're trying to read this, you should be precise to the 1 degree, okay? You should always try to be precise to 1 decimal place less than the scale that you're using is, okay? So the gram scale that we have, the little white one with the little twisty dial that you can calibrate, that one is precise to 5 grams, which is why we have to estimate to the 10th, right? We have to try to be precise to the 10th of a gram. Okay, so now we're moving on now to
number 9.
Number 9.
The specific heat of iron is roughly 3 times that of gold. Equal masses of gold and iron start out at room temperature. Heat is added to each mass at the same rate for the same amount of time. When it is all over, the gold's temperature increased by 900 degrees Celsius. What was the temperature increase of the iron? I believe it was approximately 300 degrees Celsius.
Okay, why is that?
Because if the, oh no, sorry.
No, I think you might be right.
Yes, that's actually correct. Because heat is, it's 3 times as difficult to heat, to reach the specific heat of iron, in which case, only 1/3 of that
is correct.
heat would be.
Good. So what Martin is saying is that the gold is going to be hotter, and it's going to be about 3 times hotter than the iron because of the specific heat. In order to really figure this out, what do you have to understand? What is specific heat?
Specific heat? Yes.
How does it relate to temperature change and mass, right? Same amount of energy, these kinds of things. So, yeah, so what is the equation we'd be thinking of? Q equals mc delta T, right? If the amount of energy that is given is the same, and the mass is the same, and this is different, one is 3C and the other is C, okay, that's going to be the difference. The delta T of this of the 3 times 1. Right? So this is going to be 900 divided by an extra 3. Does that make sense?
Yes.
I hope so. All right. Please read. Is this the last one?
Yes. Number 10. Why should a calorimeter always be made from an insulating material?
Can we usually say calorimeter? Calorimeter.
That's the one, yeah.
Why should it be made from an insulating material? What is a calorimeter?
A calorimeter is something that measures the calories contained within a material.
And so what do we use the calorimeter to do?
Measure potential energy.
That is the definition of a calorimeter. Okay, so it's an insulated container holding a mass of water, and the purpose is to figure out specific heat of substances. Okay, so you're using knowledge that you know. How does the way that we figure out these things? What is the equation that we're going to use? We're going to use this equation that says negative Q of an object, right? Some object is going to be the Q of the calorimeter plus the Q of the water or other liquid that's in the calorimeter, right?
Yes.
So you want this to be as inconsequential, minuscule as possible so that you can easily calculate specific heats. You want to be able to use it to calculate specific heats correctly. So, is that it for the review questions?
No, that you answered the wrong question.
What?
That's not what they asked at all.
Well, I apologize. Continue.
What they asked is why a calorimeter should be made from an insulating material.
Oh.
That's because we don't want outside energies being.
Right, since we're trying to calculate the specific heat,
yes,
if this is losing energy that we can't calculate, right? So the insulating material is going to keep the temperature as regulated as possible to prevent as much energy loss or gain from the environment. So the calorimeter is insulated to limit the contamination of the energy transfer from the environment so that we can calculate it more accurately.
Yeah.
Okay.
Now we're done.
Great. Thanks, Balloon Man.